Hi there, welcome back. We are now going to start our next theme. So let me start right away by sharing these slides and going ahead with the lectures. Okay, so we are in lecture number 20 and our next theme is the fourth theme after the machine arithmetic, then equations in one variable and a slightly longer theme on interpolation. So this is the fourth theme, which is a theme on numerical integration and differentiation, but actually we are going to say differentiation first. So that's the word which comes before the integration word. Let's start with a potential application. So in fact, I should also tell you that this is where we will now start using the things that we have learned up to now. We have learned how to find solutions to equations in one variable, which among other applications will be useful in computing eigenvalues that will come in numerical linear algebra. But interpolation is very useful, and the applications of interpolations start right away, right from our very first lecture on the fourth theme. So that's where the applications of interpolation will come. But where are the applications of numerical differentiation and integration? Why should we do numerical differentiation and numerical integration? So we are going to start with a potential application for that by indicating where it could come handy. So suppose this is the problem that we are facing, that we have a corrugated roofing and we want to get a sheet that is constructed by pressing a flat sheet of aluminum into one whose cross section has the form of a sine wave. So typically you would have seen these the sine wave like sheets which are applied on the roofs, and they are constructed out of these flat aluminum sheets by making them wavy, where the cross section, if you take, then it would look like the sine wave. So we would like to construct this such a roof. And now suppose that we are looking for a corrugated sheet which is 4 feet long, and the height, meaning the after corrugation, after making it into the sine wave, it should cover some roof which is 4 feet long. The height of each wave from the center line is 1 inch, and the wave has, say, period of approximately 2 pi inches. This is what we have. The problem of finding the length of the initial flat sheet, we will assume that the breadth is something which is very common, which is the fixed thing. Only the length is changing because of changing the shape of the surface. So the problem of finding the length of the initial flat sheet is one of determining the length of the curve. So what you can do is that you can just take the cross section, and then we want to have the curve. And once we have defined the curve, we would like to see the length of the initial flat sheet that we will have. So our curve is given by fx equal to sine x. It's in the sine wave form, and it's going from 0 to 48 because we need 4 inches. So that's what we have, and we now want to see, it's the period is 2 pi inches and so on, so we don't have to make any changes in the variable x. And the 1 inch and so on, that is also taken care by, because sine is indeed the 1 inch high curve. And so this is the integral that we will have to solve. So calculus tells you that the length can be computed by looking at 0 to 48. Integral of square root 1 plus f prime square dx. Now fx is sine x, and so its derivative is cos square x, cos x, and so the square will be cos square x. So this is 0 to 48 integration square root 1 plus cos square x dx. Now if you have done some difficult integrations in your calculus course, you may feel confident enough to solve this, but this is a particularly difficult problem. Computing this will involve elliptic integral of second kind, what are called elliptic integral of the second kind. So that already tells you that there is an elliptic integral of the first kind, and so these are both very difficult to compute, and therefore we have to develop numerical methods to compute these integrals. This is what we will have to do. So let's start with differentiation, and we observe that polynomials are going to help us. The previous themes are going to help us. Remember, I told you that polynomials are useful because whenever you have an interval, say AB, and you have a continuous function on it, then there are polynomials which approximate this continuous function uniformly. Okay, so the difference between the polynomial value and the function value can be made small over the whole interval. You actually have a polynomial. If you want the values of the polynomial to be less than the epsilon away from the function value at all points of the interval AB, then you do get such a polynomial. This is the Weierstrass theorem, the Stone-Weierstrass approximation theorem, and therefore polynomials are useful. So on one hand, polynomials give you a close enough approximation for your function. On the other hand, it's also useful. The polynomials are useful because their derivatives and integrals can be easily computed, and the evaluation is not a very difficult thing. It will be some power. It's not like sin x, cos x, exponential, or some other transcendental functions. Okay, so this is the thing. So many procedures where we are going to approximate derivatives and integrals will use polynomials which approximate the function, and the best way to approximate the function is to have some points, have some nodes, and interpolate your function by them. We will come to cubic splines also. We have seen that those give a much better approximation, but we will start with the interpolating polynomials first. Okay, so the derivative, whenever you fix any x naught, we have this formula for the derivative, which is the limit h going to 0, f x naught plus h minus f x naught upon h. So this is our formula, and therefore one very basic initial approximation to the derivative at x naught would be the right hand side, where you take h to be small enough. Okay, so at first f prime x naught is approximately equal to f of x naught plus h minus f of x naught upon h for a small enough h. But this is something which is understandable because the limit definition already tells you that whenever you want the difference of f prime x naught and the right hand side fraction to be less than epsilon, then there is an h which will do that. So you have an h small enough which does this job. But what is the error? Can we write the error in terms of h? Normally what happens, if you remember your first year calculus courses, the MA105 courses, given an epsilon, you are supposed to compute delta, and typically the epsilon will be a function of delta. You will try to reverse that and compute delta using epsilon. So we would like to get that epsilon as a function of h. We would like to get the error as a function of h. That's what we want to get here for a general function, meaning we are not looking at any particular example. Whenever you are looking at a particular example, it's easier to find epsilon and delta and the relation between them. But here we would like to do it in general. Okay, so we begin with the very first things that we have done, which is to interpolate our function at 2 points. So let's assume that our function is twice continuously differentiable, and there is this linear polynomial capital P which interpolates our function on x naught and x naught plus h. These 2 points are nearby. They are 2 points which we fix, and we are interpolating our function by the straight line which passes through these 2 points. Okay, now there is an error, and the error is written in this way. So you notice that the first two fractions that we see here, these combined give you the interpolating polynomial, and here you have the error x minus x naught x minus x1 upon 2, the second derivative of the function at some xi x, where xi x lands between x naught and x naught plus h. This is what we have. So now what we do is that we take the derivative of this function. Just one sec. All right, we are back. So this is the error that we have for where xi x is some unknown quantity. And now what we are going to do is to take derivative of both the sides. So the left hand side will be f prime at x and the right hand side will give you some derivative. The derivative of the first two terms can be computed very easily. This is f of x naught upon minus h, and you have to simply take the derivative of this linear factor, which is 1. So this will be f of x naught upon minus h, and you have f of x naught plus h upon h. So this is going to give you the required formula, f of x naught plus h minus f of x naught upon h. And then we have to take the derivative of the right hand side. So the derivative of the right hand side, this is a function which is a multiple of two functions really. You have the polynomial, which is x minus x naught minus h upon 2. This is one polynomial, and you have f double prime at xi x. All right, so taking the derivative of this product will be taking the derivative of the first term into keeping the second term as it is, and then taking the first term as it is multiplied by the derivative of the second term, and that's where the problem comes. But let's see how we get it. We differentiate the above equation and the derivative will give us this. I told you that f of x naught plus h minus fx naught upon h. This is the formula for the derivative of the interpolating polynomial. Here we are taking the derivative of the first term of the product of those two terms and keeping the double derivative at xi x as it is. And then we get the d by dx of f double prime xi x. That was the thing that we were not really looking forward to, because first of all, xi x is some random function. We have been able to compute these errors in some very special cases. I actually computed the error in one particular case some time back. But even then, we don't know whether f prime composed with this xi x is a function which is even differentiable. We hope that it is differentiable. Typically, all our functions are infinitely differentiable. So this will be differentiable, but how this thing behaves is something that is not known to us. However, don't worry, because what happens is that we have this x minus x naught here. So when you put x equal to x naught, this second term involving the derivative of f double prime xi x vanishes. And what do we get? We get this term, the first term will come as it is. This x minus x naught also vanishes, and so you simply get h by 2. So the error becomes h by 2 f double prime xi x. Now this is somewhat manageable, because it tells you that for small enough h, something that we already knew, the quotient f of x plus h minus fx naught upon h is an approximation to the derivative at x naught. But it also tells you that the error is less than or equal to m mod h by 2, where capital M is an upper bound for the double derivative on x naught and x naught plus h. So we know that the derivative can be approximated by the quantity f of x naught plus h minus fx naught upon h, and we also know that the error is bounded above by capital M into mod h upon 2. All right, so let's do an example. Every time we compute some formula, we would like to do an example, but let me also tell you how this thing looks like when you are looking at the picture. So we have this line here, which is given by whose slope is f prime x naught. But then you have taken this point x naught plus h. We plot it here on the graph of the function and then join these two by a line. And we are computing the slope, which is f of x naught plus h minus fx naught upon h. That's the slope that we are computing, which happen to be the derivative of the interpolating polynomial. And now the point is that h can be positive or h can be negative. So whenever h is positive, we call the formula to be the forward difference formula. Else we call it the backward difference formula. Okay, so this is what we have. So let's do an example. We compute the derivative of something we know so that we can look at the error and approximate the error. So fx is the natural logarithm of x, and let's take x naught to be 1.8. Okay, we will use forward difference formula, which will give you that the derivative at 1.8 is f 1.8 plus h minus f 1.8 whole thing divided by h. This is the formula. We take h to be 0.1. It's a very crude h because your x naught is 1.8, which is a very small number really, and you are taking h to be something which is of the factor of say 1 upon 20 for the h. Typically you would like to have h to be very small, but even for this h we are getting reasonable answers. So then the approximation will be the natural logarithm of 1.8 plus 0.1, so that's going to be 1.9. We have to remove the natural logarithm of 1.8 from that and divide by h, which is 0.1. So the answer turns out to be, taking first few digits, it's 0.540672227. And then the error can be computed because it is mod h f double prime at xi upon 2 on the whole interval 1.8 to 1.9. But the derivative of fx is 1 upon x and double derivative is minus 1 upon x square. So when you put it into mod, it's just 1 upon x square. So the derivative, this formula, mod of h double derivative at xi divided by 2 is simply mod h upon 2 xi square. And you are looking at it from 1.8 to 1.8 plus h. Remember, h is positive. We are taking the forward difference formula. And then the error will be bounded above by this particular value where xi is the least in that interval, which is 1.8. So this is less than or equal to 0.1. So this is going to be strictly less than because our xi is strictly between 1.8 and 1.9. Every time xi will be strictly between these 2 points, right? So that's why we have this strict inequality 0.1, which is the modulus of h, upon 2 into 1.8 square, and that turns out to be 0.015. So not a bad approximation really, because we were looking at h being something like 1 upon 20 of the point x naught that you have. So it's not a very small number compared to the value of your x naught, and still we have got a value which by our error calculation is correct up to the first digit after decimal point. And even the second, if you look at the second digit of the error, that is 1. Even if you round it up, it's going to be 2. So that's not too bad again. Okay, so let's now plot a table for few such values of the step, which is h. We will of course decrease h from time to time. So the table will have values for h, the function value at 1.8 plus h, then the approximation to the derivative, and finally we will have the error. Of course, as you make h smaller and smaller, the error will become smaller and smaller. This is the calculation that we have already done. Now if you take 0.08 for your h, then you see that once again you have 0.54, which is equal to the first 2 digits that we got in the very first approximation, and the error has become slightly smaller, not too much but slightly. If you go to 0.05 as the value of h, then the error is now smaller by 2. The error gives you 0 as the first 2 digits after decimal point. And a few more computations tell you that if you are looking at the h to be 0.01, which is 1 by 10 of the original h that we did in the previous slide, then the error is also going to be 1 by h, because the error is just a multiple of mod h really. So our answer is now correct for 2 decimal digits. And then you can guess that if you keep on reducing the error by a factor of 10, you are going to get 5, 5, 5, 5, 5, and so on. And in fact, we know the value. We know what the correct value should be, because the derivative is 1 upon x and x naught is 1 upon 1.8. So you have to just compute 1 upon 1.8, which happens to be roughly 1 by 2, which is 0.5, and this is slightly 1.8 is slightly smaller than 2, so 1 upon 1.8 is going to be slightly bigger than 1 by 2, and then it becomes 0.5555. So that's a good enough approximation that we get for that at h equal to 0.01. So the initial guess for our derivative has proved correct, a very good guess, but we can do better than this. What is the better thing that we can do? We have used the interpolating polynomial for only 2 points, 2 nodes. So this encourages us to use interpolating polynomials for higher number of nodes. So suppose now let's look at the error formula given by the interpolating polynomial for n plus 1 distinct nodes, that we will also need to assume that our function is n plus 1 times continuously differentiable on this interval I, which is a standard assumption. Then the error is written in the following way. So the error will have that x minus x naught up to x minus xn will be there in the numerator, and you divide that product by n plus 1 factorial, and then you have the n plus 1th derivative of some xi x. This is what we have. Okay, and this is the interpolating polynomial, which is the linear combination of the Lagrange polynomials, which you know quite well. We are going to take derivatives for this. The derivative will give you derivative for the Lagrange polynomials, and then the derivative for the error term. Once again, if you put x equal to xj, then the difficult term, which will be the derivative of the n plus 1th derivative of the function at xi x, that will vanish. And so what we get is that f prime with the derivative of our function at xj is summation k from 0 to n plus 1 f xk lk prime at xj. Lk, remember, is the kth Lagrange interpolation polynomial for the distinct nodes x0 up to xn. Evaluate it on xj, and plus the n plus 1th derivative of the function evaluated on xi xj upon n plus 1 factorial into the product xj minus xk, where you are running k from 0 to n, but k not equal to j. Okay, because when you take this particular term, which is a product of x minus xj, you take the derivative, it will be the particular sum where you are going to take derivative of any one particular factor and keep the other factors as they are. So if you take the factor x minus xj and take that derivative, it's going to give you the remaining factors x minus xk, where k is not equal to j, and putting x equal to xj gives you this particular form. If you were taking the factor to be x minus xk, where k is now not equal to xj, then x minus xj survives in the formula, and by putting x equal to xj, you are going to get 0. So the derivative of that by putting the value x equal to xj is this particular formula. So this is called the n plus 1 point formula to approximate the derivative of the function f at xj. Again, we cannot keep doing this for every n and seeing the errors. There are some very standard formulae. There are some of the very common formulae. The common formulae are 3-point formula, where you will have n equal to 2, and 5-point formula. Don't confuse with the novel 5-point someone. This is the 5-point formula for computing the derivative f prime at xj. So how would the formula look for the 3-point formula? So we are going to take n equal to 2. We will have x0, x1, x2. It will tell you that the derivative at the point xj is fx0, that particular term, which is 2xj minus x1 minus x2 upon x0 minus x1 x0 minus x2, plus a similar term for f of x1, a similar term for f of x2. These are coming from the derivatives of the Lagrange polynomials, and then you are putting particular values for x equal to xj. This is what you are getting. And finally the error term, which is the third derivative at xi j. Xi j is the point xi x where x is xj. Instead of introducing that new difficult notation xi xj, we simply call it xi j, and then we divide by 6, which is the 3 factorial product xj minus xk. This is what we have. So in particular, if you were to use this formula for x0, x1 and x2, you will get simpler formulae, but it's also very useful to take these nodes to be equally spaced. So if you let x1 to be x0 plus h and x2 to be x0 plus 2h, then these formulae become simpler. Let me write them down in the next slide. So in particular, the formula for the derivative at x0 is this particular formula. You have 1 upon h, which is now taken out, and it's 1 upon h is coming out because this is coming from the differences. So here you have x0 minus x1, which is going to be h or minus h, and here you have minus 2h, so the minus minus gets cancelled, and here you have h, this is minus h. So some nice formulae come out. There will be an h coming also from the numerator, so you are not going to get h square from the denominator. The h cancels one term of h, and so ultimately you get something like this: minus 3 by 2 f of x0 plus 2 f of x1 minus 1 by 2 f of x2. So we see that for the point which is that point which is x0, the contribution seems to be 3 by 2, but it's on the negative side. Then you have 2 fx1, and then for the point which is farther away, it is smaller, it's minus 1 by 2. And then you have this error h square by 3. The error had earlier h square by 6, which has now become simpler. It's h square by 3 f cube at xi naught. There is also this midpoint formula, the formula for the point which is in the middle, and this is a particularly simpler formula. And finally you have the formula for the derivative at x2. Now note that there is a very nice symmetry in the formula for the derivative at x0 and the formula for the derivative at x2, because you have 3 by 2 for f of x2 in the f of x0 in the formula for f of x0. The f of x2 formula has the 3 by 2 coefficient for f of x2. The coefficient of f of x1 in both of them is 2 with a negative sign. So the sign is also changing because you are going from, instead of going in the positive direction, you are coming in the negative direction. So the sign is changing. And also you have 1 by 2 for f of x2 in the formula for f prime x0, and the coefficient for f of x0 in the formula for f prime x2, it is 1 by 2. So there is this particular symmetry, and of course the error formula will not change. It is simply h cube h square. So h square or minus h square remains the same. So what we are now going to do is to think that we were actually computing not the derivative at x0 but for the derivative at x1. So our x1 will be new x0, and the x0 which was there, that will now become x0 minus h, and the x2 will become x0 plus h. So instead of looking at x0 plus h, x0 plus 2h, we may look at x0 minus h, x0 and x0 plus h. Or for the x2, you may actually think of it as x0 minus 2h, x0 minus h, and x0. But because of the symmetry, the x0 and x2 situations are similar. So essentially we are going to get only two formulae. We will have a formula for the end point, which is the x0 or x2, and we have a formula for the midpoint. So we are going to write this formulae assuming that the point xj is our x0 and adjust the remaining terms with the help of h. That's what we are going to do, and writing that we get these 2 points. This is the formula for the end point. This is 1 upon 2h. The 2 is also now taken common. So 1 upon 2h minus 3 f of x naught plus 4 f of x naught plus h minus f of x naught plus 2h. And the error, as earlier, it is h square by 3. The third derivative at xi naught. And here xi naught is between x naught and x naught plus 2h. And we also have the midpoint formula, which is the f prime x naught equal to 1 upon 2h, f of x naught plus h minus f of x naught minus h minus h square by 6, the third derivative at xi naught. Here xi naught lies between x naught minus h and x naught plus h. Now, what do we see from these two formulae? These two formulae tell us that the endpoint formula is slightly more complicated, whereas the midpoint formula is better, it's simpler, and even the error is better. The errors are in the order of h square for both of them, but the error for the midpoint formula is half of the error of the endpoint formula. And that is also very natural, because when you are using the endpoint formula, you are using data on only one side of the function. The derivative should have something to do with both the sides. And so the midpoint formula takes care of both sides. You know, you're going h distance ahead and h distance backward, and then you are trying to take the slope of the line. So the geometry looks like this, that instead of taking the slope of the original tangent, what you are doing is that you are going ahead by h, you are going behind by h, joining these two by a straight line, and then taking the slope of that line. So you were actually going to take the quadric passing through the function values at x naught minus h, x naught and x naught plus h, and then take the derivative, which happens to be the slope of the line joining these two endpoints, and that gives you a much better approximation. So in our next lecture, we are going to do some examples using the 3-point formula, also touch upon the 5-point formula, and then go ahead to the numerical integration. So sit tight. This is going to be a very, very interesting ride. Thank you.